Hello. Can you all hear me? Right on. Well, thank you very much for coming today. And my name is Leo Dirac. I am Senior Principal Engineer in AWS working on SageMaker. And we're lucky to be joined today by Luis Canet, who is Vice President of Data Science and Engineering with 21st Century Fox. And he's going to be talking about his experiences using SageMaker. But to start with, I'm going to give you some background on SageMaker generally and how you can build, train, and deploy models with it. Then, after talking about some of the features, we'll do a technical deep dive into how you deploy a trained model at scale. We'll talk about creating endpoints, how to do deployments, automatic scaling. We'll actually show you the APIs. We'll get into the nitty-gritty on that one. Since this is a 400-level session, we don't want to leave you lacking for details on this. Then I'll hand it over to Luis, who will talk about using machine learning at 21st Century Fox. And he'll tell you about how they have integrated Spark and Amazon SageMaker to be able to solve their problems at scale. So to start with, I'll just give you an overview of the entire Amazon machine learning stack. And this is built in 3 layers, really. At the top, we have the high-level AI services. And these are services which are designed to be the easiest to use on the most common AI problems. And these are usable by people without machine learning backgrounds, without expertise in data science, on problems in vision, speech, language, and conversation. So if you have an image, you can just send that image into Amazon Recognition Image, and it will understand it using the latest deep learning technology, highly trained models that are tuned to solve the most common tasks in understanding images, like facial recognition, object detection, classification. Same kinds of capabilities with video. In speech, Amazon Poly and Amazon Transcribe can take text and turn it to speech, or the other way around. And so these common AI tasks are just automatically available. With language, you can translate between languages, you can do natural language comprehension, understand what's going on inside of textual documents, and create chatbots. All of these high-level AI services are available for people without data science expertise. And so we've taken some of the hardest and most common problems and just made them available to you at a single API call. If you need to do something that's a little outside of the bounds of what those services do, then you can pop down a layer on the stack to the ML services, which is really where Amazon SageMaker shines. So here, you can create your own machine learning models on your own data. You can build basically anything you want. We have a broad suite of capabilities ranging from very simple to use to extremely custom, and we'll dive into the details on that in just a bit. But if even SageMaker is too restrictive for you, you can always drop down to the bottom layer of the stack, which is the frameworks and the infrastructure that all of this stuff runs on. So there's the software libraries like TensorFlow and PyTorch and MXNet and Chainer, which make it possible to build the most advanced deep learning applications in the world. And they all run on Amazon infrastructure, such as the super fast P3 GPU instances, or the super fast CPU instances in the C5 and M5 families, or even custom silicon through FPGAs. And if you need the absolute utmost control over what you're doing, you can always pop down to that level and run things directly. Overall, machine learning is still extremely complicated. The entire workflow involves a huge number of steps. Getting your data together, picking which algorithm you're going to use and optimizing it, figuring out the training environment that you're going to use this algorithm in. And then for even experienced scientists with PhDs, training and tuning the model is still a trial and error process. It can take a very long time. Once you've done that, deploying it into production involves figuring out all sorts of complex systems to make your system reliable. And then you need to manage that and make sure that thing is always available. SageMaker makes machine learning much simpler. We have features like one-click deployment. From the console, you can just click a button to train a machine learning model and click another button to deploy it to a scalable production endpoint. We have built-in algorithms that are 10 times faster than open source alternatives and scale out to as large a data set as you need. And all of this makes it possible for you to build applications for predictive insights to enable advanced decision-making for whatever your business problem is. So the basic pattern that SageMaker uses to simplify machine learning is build, train, deploy. So what do I mean by that? First, you need an environment to build in, and usually this is a notebook instance. Jupyter notebooks are a lot like the IDEs for data scientists today. So Amazon SageMaker has these fully managed notebook instances where you can create a customized environment with libraries that you need, access to your data in a safe, secure manner, and control everything from there. Or you can call the exact same APIs from your own device, whether it's a laptop or a workstation or anything else. Everything that you can do from a fully managed notebook, you can also do from anywhere else through the public AWS APIs. Then once you've figured out your model, you need to train it. And SageMaker offers a fully managed training environment which is distributed. It can scale out to as much hardware as you need and has extremely high performance I/O, access to S3, which has all the data that you'll ever need, and is all fully managed and repeatable so that the training process is reliable. And once your model is trained, you deploy it to whatever endpoint you want. So if what you need is low latency prediction, you can deploy it to a real-time endpoint. If what you need is to get through a large volume of data as fast as possible, then you can use a batch transform, which is optimized for throughput instead of latency. Or you can send it to an edge device, IoT device through AWS Greengrass or through DeepLens. So some of the features that make it possible to build advanced machine learning models in SageMaker are the built-in algorithms. So these algorithms, click, there we go, are designed for both speed and scale. And so we have an ever-increasing number of algorithms that are fully supported inside of SageMaker for supervised learning problems, unsupervised learning problems, domain-specific tasks such as computer vision and natural language processing. We just announced a new algorithm that I've been helping with called Object-to-Vec that can take sequences of data and unique identifying tokens and learn an embedding space from them. And all of these are designed to scale out to very large data sets and to run significantly faster than what's available in open source alternatives. And a great thing about all of these fully managed first-party algorithms is that you can train models on them without writing a single line of code. You can do all this from the console just by pointing it at your data and making a single API call, and then the training just happens for you. If these do exactly what you want, that's awesome. They're pretty flexible. But if you need additional flexibility, if you want to do something not quite what they are, what they're offering, then you can use one of the frameworks. So we have managed supported versions of TensorFlow, PyTorch, MXNet, and Chainer. And these allow you to write the small amount of Python code that you need to define your model and inject that code into a managed optimized container, which is built to run at maximum speed and to automatically scale out to as many machines as you need to handle very large quantities of data. And the code that generates these containers is all open source. It's up on GitHub. So if you want to see how we get PyTorch to scale out to all the machines you need, you can just go to GitHub and you can see how we do that, and you can clone it and fork it, do whatever you want. And all of these are available also in local mode, so you can download these containers and run them on your notebook instance or even on your laptop and get very quick iteration to test how your code is working before you deploy it up to SageMaker to run it at scale on the full data set. Now, if these frameworks still don't do exactly what you want, you can always go down a layer inside SageMaker and bring your own container. So you can always build your own Docker container that has whatever code you want. And if you're a fan of probabilistic programming languages like Stan, or you're an R user, or you want to write machine learning code in Julia or what have you, you can compile all of that into your own Docker container that meets whatever enterprise requirements your organization has, and you can do all of your training on that Docker container. And it still happens inside of the fully managed and secure SageMaker environment. And all three of these, no matter how you get your algorithm, can be used with the automatic model tuning feature. I've worked a lot on this feature myself, and I find it incredibly useful. Machine learning systems always have these hyperparameters like learning rate or regularization or the number of layers in a neural network or what have you. Almost nobody knows what the right setting is for these in general or even what they do a lot of the time. So instead of just using trial and error, the automatic model tuner will try these for you in parallel. You can say, go run 500 jobs and do them 10 at a time and figure out what the best settings are for each of these hyperparameters. And it'll do all of that, again, in a fully managed and scalable environment for you. This works regardless of whether you're using a built-in algorithm, something you wrote in one of our frameworks, or if you're supplying your entire Docker container yourself. OK, so after that overview of how Amazon SageMaker works generally, let's dive into real-time deployments. So again, real-time deployments means that you're setting up something, an endpoint that has low latency. So this is what you're going to want to do if your machine learning model is being used on a website or in a mobile app where you want the response to come back in a fraction of a second, in just milliseconds. And this is not what you want to do, say, if you have a big CSV file or a big data file that you want to make predictions on, if you want to run it against every record in a database, for example. In that case, the batch transform feature is more appropriate. That's optimized for throughput, and will get through that big data set as fast as possible. But the latency on every prediction will be much higher. Here, we're talking about low latency real-time deployment. So the entity that you use for this kind of real-time deployment is an endpoint. And you can create one of these from a click on the console or by making an API call. And this sets up a REST API endpoint so that you can make predictions from any programming language. You can call it from anywhere you want, and it will run the code that was created in that training process, regardless of whether it came from an Amazon first-party algorithm or your own container or a framework. It all works the same. And these endpoints are highly scalable, have very high reliability, and very high throughput. So the API to create one of these endpoints is up here on the screen. And what I'm showing this API in is the AWS command line interface, or CLI. So you can literally type this command from your terminal and have it run. And a nice thing about the CLI is that the format of it exactly mirrors the API call that you would make from any language using the AWS SDK. So SageMaker is the namespace of the service, of course. This is the create model API. And then everything after that are the parameters. And in the case where the parameters take a data structure in, it's passed in as a JSON block, as you can see, like for primary container here. So let's talk about this create model API. So this is the first step to creating a highly scalable endpoint. So the first thing you have to do is bind together the data and the code that you need to do your predictions. So the data is specified in that model data URL, and this is the location in S3 of the parameters for your machine learning model as it was created in the training process. And then the image is the Docker image that has the code for running the hosting service. So if you're using our framework or a first-party algorithm, then that Docker image is fully managed and just works for you. And if you use the Python SDK, it'll even be set for you automatically. If you're bringing your own container, then you probably need to build the image yourself, which is going to run there. But once you've created this model, you've bound together the code to do the serving, along with the data, which is the machine learning model parameters that were learned, and you specify the execution role to say what permissions that this thing is going to have as it's running. Now, we need to say more than that, right? Because we haven't said what kind of machines it's going to run on or how many of them. And for that, we need to create an endpoint config. And the endpoint config is another thing that says the configuration of how this machine learning model is going to be served. And there's some other, you give it a name, and there's some weights and variants that I'll talk about a little bit later. But the key thing for now is that this specifies the kind of hardware that the thing will run on. Once you've created the endpoint configuration, creating an actual endpoint is a very simple API call. You just say create endpoint, give it a name, and point it at the config. So now you have an endpoint, which is configured with this endpoint config. The endpoint config has the name of the model, which you created in the first call. And now, once you've done all of this, SageMaker turns on the number of instances that you talked about. So here we say we want M4X large and 2 of them to start with. And these get instantiated and loaded with your container and loaded with your model. And now you have a low latency endpoint available. So once it's there, you can do a bunch of interesting things with it. Let's say that your science team has come up with a new model and they want to update the endpoint. So it's possible to very easily do a blue-green deployment where you turn on new machines before turning off the old ones. And once the new ones are warmed up and ready to go, they get slotted in behind the load balancer, and predictions get routed to these new machines with 0 downtime and 0 interruption to live service. That's one thing I'll show you how to do. And then another thing you can do is actually deploy more than one model behind the same endpoint. So let's say that you have this new model called Model 2, which is some fancy neural network that the science team has come up with to replace the old model, which was, say, a decision tree using XGBoost. So you want to switch over to this. So you create a new model, which binds together, again, the data with the code. The data in this case is the weights of the neural network. And the code is something like TensorFlow serving that knows how to serve that model. Give it permissions. Say what kinds of machines it's going to run on. And you might want to use GPU instances for the lowest latency if you're using a neural network here, and have a different set of hardware configuration than your old model. And then you can call update endpoint, pointing to that same endpoint, my endpoint, and give it this new model configuration. And SageMaker will turn on these new instances for you, load this new model with the code and the data on it, and once it's available, live swap over the traffic to it with 0 interruption. This is a great way to swap out a model all at once, if that's what you want to do. So this is great if you're in a production setting, such as one where there's new data showing up all the time. So I used to work in the retail part of Amazon, the bookstore, as we playfully call it here in AWS. And we would build models to predict what kinds of products people would likely be interested in for recommender systems. And so every week, we would train new models and swap them out for the old ones. And we had a bunch of complex infrastructure for managing this. And back then, if we had SageMaker, this would have been much, much easier, because we could just call update endpoint, and the new endpoint would go into production with 0 downtime. This also makes it very easy to try out new and improved algorithms that you think might be better than the old one. But sometimes it's not such a good idea to just instantly turn off that old reliable decision tree that you've been running for a long time and send all your customers this fancy new neural network all at once. And sure, maybe it performs well on your held out validation set, but is it really going to work in real life? Maybe. Hard to know until you try it. So a safer thing to do is to do a 2-model endpoint configuration. And so now you're starting to see some of the power in that endpoint config object that I glossed over earlier. So this parameter called production variants, you can actually specify more than one of them. And so here I've created a production variant with 2 different variants, one called Model 1 traffic and the other one called Model 2 traffic. And I'm setting it so that 95% of the traffic is going to that tried and true XGBoost algorithm, and only 5% of the traffic is going to the fancy new neural network. And this way, we can put that fancy new model into production and see how it does without risking the behavior, some poor behavior on all of our customers. Excuse me, 1 second. Thanks. Okay, so, and actually I left out the automatic step, which is once you've created that endpoint, you need to call update endpoint, and now SageMaker will turn on 2 more instances with with model 2 and start routing just 5% of the traffic over to that new model. And this allows you to do things like A/B testing, comparison, and check how a new model is doing before fully committing to it. Let's say you do this for a while, seems to be doing all right, like nothing obviously wrong, but you're not really getting traffic to it to say for sure that it's doing better than the old one. So now, without taking anything down, you can quickly update the weights on these variants and take the weight from Model 1 from 95 down to 5. And now Model 1 and Model 2 both have a weight of 5, and so they're each going to get half the traffic. Now you can do a fair comparison between these two. And this is a very simple API call. And again, the routing layer inside SageMaker automatically adjusts the amount of traffic that's needed to go to each of these models so you can see how each of them are doing. Now, that the amount of traffic that's going to that neural network now might get overwhelmed because it's just, we went from 5% to 50% with that update configuration method. So those 2 machines might not be enough. So you might need to automatically scale your endpoint. So SageMaker makes this easy straight from the console. So you can specify when you're setting up an endpoint how many machines you want to scale between. So here we're saying that we want at least 2 and up to 5. And you need to tell SageMaker how it's going to scale, what criterion it's going to use to scale on. And here we're using target invocations per second, which is the number of queries per second, transactions per second, predictions per second that each machine is making. And this is something that we recommend using invocations per second because it's generally more reliable than other measures that you could use like CPU utilization or GPU or memory or what have you. So you need to do some tests on your specific model and on the instance type that you're interested in to figure out what's a good number. And in this one, we decided that 800 was a good amount. And we can specify the number of seconds to cool down between a scale up or a scale down event to prevent it from flapping back and forth. Excuse me. Automatic scaling is important, of course, because the amount of traffic that hits any real-time service tends to vary with the number of people who are awake or all sorts of things. There's typically a daily cycle, a weekly cycle. If you have enough machines turned on to handle peak traffic all the time, you're wasting money. And if the traffic were to spike beyond what you're looking for, then some of your customers are going to have a bad experience. With automatic scaling enabled, the number of invocations will adjust based on, the number of invocations per instance will adjust based on the traffic. So here's an actual plot of when we're testing this. And to begin with, there's 1 machine turned on, and so the orange and blue lines are on top of each other. So you just see the orange one. The total number of invocations is the same as the number of invocations per second. Then when it passes up about above 3,000 or so, then a second machine turns on, and now the number of invocations per instance gets cut in half, even though the total amount of traffic stays high. And so you can pick whatever scaling criteria you want to be able to scale reliably. Different algorithms are different, especially when you start writing your own code in a framework or in your own container. And whatever metric is posted to CloudWatch metric, you can use to scale these endpoints. So if you want to set up an automatic scaling policy yourself using the API, this is what it looks like. We're going to use the AWS application auto-scaling feature, and we're going to call the API called register scalable target. And we're going to point it to SageMaker, give it the name of our endpoint, and tell it to adjust the desired instance count between 2 and 5. And then we have to create this policy. And this is a complex policy which gives you a ton of control. If you do this through the console, then it's going to set up a bunch of common defaults for you. And this one's actually a little bit different. Here, instead of invocations per second, we are targeting CPU utilization. And we're saying we want 50% utilization, which is a reasonable amount. If you're above that, then your machines are running pretty hot. Maybe you want to add some more. If you're below that, you probably have more machines you need, so we can turn some down. And so here it is again, overlaying that same graph of invocations against the CPU utilization. So this machine was, I think, an M512XL, so it could get up to 1,200% total utilization, or 50% per CPU. And as you see, once it crossed over about half utilization of each of those cores, then a second machine got turned on, and the invocations per instance went down. So that concludes my deep dive into real-time hosting at scale. And now I'll pass it over to Luis, who will talk about using Amazon SageMaker at 21st Century Fox.
All right. Thank you. Thanks a lot, Leo. All right, good afternoon to everyone. As Leo mentioned, my name is Luis Canet, and I'm the VP of Data Science and Engineering at 21st Century Fox. So at 21st Century Fox, I'm part of a team that is called the Fox Data Analytics team. And we're a center of excellence for data science and analytics across the entire 21st Century Fox organization. So my team specifically is focused on identifying and executing on opportunities to apply AI and machine learning across these three main areas. The first one are commercial opportunities. So how can we create models that help us optimize our current revenue streams and identify new revenue streams for our organization? The second one is consumer analytics. So how can we identify behavioral patterns in our consumers across all the digital properties that we have and utilize those to be able to build recommender systems and other personalized experiences across the different applications that we have? And finally is content. So these one are things like automatically extracting metadata information from all the media assets that we have stored, and then doing things like automatic content creation. An example of that would be, so we, for example, have on Fox Sports. So game highlights is a very manual process. So we're trying to build models that take all this metadata about the games and use those to automatically create highlights of those games. So as you can see, I mean, we have a wide variety of problems, machine learning problems that we're trying to solve. And on top of that, we're a global organization with more than 1 billion subscribers. We're in more than 170 countries, and we own more than 500 channels between broadcast, cable, and digital channels. So scale is something that it's very important for us. And as our data science team started to grow, there was a need to build a centralized data science workbench that will help us standardize on our data science development process, so that we could improve the productivity of our team. So some of the requirements that we have for that were this environment needed to be scalable, and that means for data preparation, training, and deployment of our models. It needed to have a seamless integration with our AWS Data Hub. So before starting this team, there was a huge effort to build our centralized data hub in the AWS cloud. It also needed to be flexible, to be able to accommodate multiple frameworks. So we didn't want our data science team to be just focused on using a specific set of tools. We wanted to give them the ability to use as many as they wanted. It had to be multi-user. So we have multiple data scientists working on different problems. So we wanted to have the ability to set up security and multi-tenancy across this environment. It also needed to be centralized, so that all of our data science team members could collaborate among them. So the cloud was a pretty good fit for that. And we also wanted to minimize the engineering overhead that we have. So we wanted our data science team members to be as autonomous as possible and not have to rely on either the architecture team or the engineering team to do a lot of their development. So at the time where our team started to grow, SageMaker was announced, so we thought it was a pretty good solution for what we were trying to do. So we gave it a try, and we've been working on fine-tuning the out-of-the-box capabilities that come with SageMaker to make it work for us and to also improve our productivity using this tool. So it took us several iterations to get to where we are today, and my goal for today is to share with you some of the challenges that we run into by using SageMaker in the real world and some of the solutions that we arrived to. So the first challenge is data wrangling at scale. So SageMaker does a really good job at training models at scale as well as deploying them at scale. But when it comes to data processing, you need to rely on other tools like EMR and Spark. So we didn't want our data engineering team to have to rely every time on our data engineering team to do all the data preparation for us so that we could feed it into our models. So since our data science team was very familiar with Python, and they were very familiar with Jupyter Notebooks, we decided to integrate SageMaker with EMR so that they could do data wrangling and data modeling in the same notebook as a seamless experience for them. So the process to integrate SageMaker with EMR is kind of a four-step process, and there's a really great blog post that talks about the specific steps that you need to follow, but it's basically a four-step process. First, you need to create an EMR cluster and make sure that both Spark and Livy services are enabled. Then you need to make sure that the security groups that are open ports to communicate between SageMaker and EMR, specifically the port 8998, which is the standard for Spark. Then when you create a new SageMaker instance, you need to make sure that that SageMaker instance is within the same VPC as your EMR, or it has a good way of connecting to it. And then finally, you need to configure your SageMaker instance to point to the master node in your EMR cluster. In this case, it would look very similar to what you have here in the right. You would just replace the IP address that we have in here with the specific IP address of your EMR master node. So once you do that, you can basically go to create a new notebook instance, click on the first option, which is PySpark, Spark Magic, and then that gives you out of the box a notebook where you can actually invoke Spark context and start utilizing it as if you were writing any other Spark job, but in this case, it has the interactivity that comes out of the box with the Jupyter Notebook. So that gave us an opportunity to start leveraging Jupyter Notebooks to interact with Spark within SageMaker, everything in the cloud. But once we had this, we ran into and before we go into that, I wanted to explain a little bit how this works under the hood, because it will help explain the challenges that we run into afterwards. So as opposed to when you're using an out-of-the-box SageMaker instance, where the Python code that you have in your Jupyter Notebook, it's being executed in that same instance. When you connect your SageMaker notebook to an EMR cluster, your code is actually not being executed in your SageMaker instance. What is happening is that every cell that you execute gets transmitted through HTTP into a Livy server, which is a service that allows Spark to be accessed through an HTTP interface, and then your code is actually being executed within the EMR cluster. And that's important because it causes issues like this. So when you're trying to use some of the very widely used libraries in the machine learning world, like pandas, to do data wrangling, and you want to combine that with Spark, then you realize that that library is actually not available. And the reason why this is happening, even though those libraries are available in SageMaker, when you connect SageMaker to EMR, those libraries disappear because your code is actually being executed in the EMR cluster, which has plain vanilla Python. So one of the solutions that we did for that was deploying Python Anaconda across all of our different nodes as the standard Python distribution being used by EMR. So for those of you who are not familiar, Python Anaconda is a Python distribution that comes out of the box with a lot of different data science libraries pre-installed. So that's why we took it as an initial point for us to start having access on the EMR cluster to a lot of the data science libraries that we use. And I mean, the process is pretty simple. I mean, you just, on the left, you just have the standard steps on how to install Python Anaconda in any Linux machine, where you just get the package, execute the installer, and just configure your profile to use that as your default Python. And then in the right, you have some additional steps that are very, very important for you to be able to leverage, to configure your EMR cluster to leverage that new Python version that you have installed. So first of all, you need to make sure that within your Spark configuration, you add that in the master node, you add that configuration step that tells Spark what is the default Python distribution through the Spark PySpark Python configuration parameter. And second, you actually need to make sure that your Libby server, which is the server that allows you to communicate to Spark through HTTP, also knows that your Python distribution is the one that you have just installed. So that solves our initial problem of being able to leverage additional data science libraries within EMR on SageMaker. But then we also ran into another challenge. So we were using Spark to be able to do a lot of the data wrangling. So when we were creating complex data objects like Spark vector, then it was really hard to feed that vector into SageMaker. SageMaker, by default, takes in either CSV files or some other files that are specific to the model that you're trying to train. So for example, for XGBoost, it can take either CSV or another format that is called libsvn. So if you want to take a vector and write it as a CSV file, you actually need to expand it into multiple columns, which is a very cumbersome process, and it also takes a lot of processing power. But writing that Spark data frame into libsvn format is not simple either. So one of the solutions that we got to, in order for us to be able to seamlessly take a Spark data frame or Spark object and feed it directly into our SageMaker models, was by installing a library in the EMR cluster that is called SageMaker PySpark. So SageMaker PySpark, what it does is it allows you to access all the SageMaker services directly from your EMR cluster. So, and what it does under the hood is when you have a Spark data frame and you feed it as a training object to your SageMaker, it actually writes that object in the format that SageMaker needs onto an S3 bucket. And then when it finishes training, it actually deletes those files that it has created with the new format. So that allowed us to go from do all of our data wrangling, create our vectors or features, and then feed those directly into SageMaker so that it could be trained at the scale and also deployed at scale. So another of the challenges that we had is that when you're working with big data, sometimes it takes a little bit of time for it to be processed. So by default, when we started connecting to the EMR cluster and we had a job that was running for more than 10 minutes, we started to get this error. And the biggest challenge is that by default, Libby comes out with a 10-minute timeout. So if your job runs for more than 10 minutes, then your Jupyter notebook that you're interacting with will die if your cell took more than 10 minutes to run, and you have to start everything from scratch again. So the solution to solve this problem is just go to your master node in your EMR cluster, go to the Libby configuration, and just increase your timeout to something much bigger. For example, 10 hours is what we have in here. So, I mean, these smaller steps, there are a lot of other things that we've done to configure this environment to make our team more productive by using SageMaker, but these are some of the things that cost us the most pain at the beginning, so I wanted to share them with you. But after improving the operational workflow within SageMaker, these are some of the things that we've seen as a gain for our team. So the technology and process has been adapted for our team, so a standardization and centralization of the data science work has improved. Like before, each of the data scientists had their own environment. By using this cloud-based SageMaker environment, everybody's more able to share their work with each other. It has also increased the scale for our models. It has increased the efficiency of our data science work. It has helped us move from large dedicated instances that we use to train our models to a scalable cloud infrastructure. And it has also reduced the cost that we had for training our models. Because as Leo has mentioned before, SageMaker, when you're training a model, it actually spins up whatever instances it needs to train, and then it shuts them down. So, and another thing that has helped us a lot is the out-of-the-box recipes that come with SageMaker that solve a lot of the very common data science modeling use cases. And that's pretty much it. I just wanted to mention before we close that a lot of these improvements that we've done to our data science workbench environment have been done in partnership with the AWS ProServe team, which is a really great resource to help any company accelerate the adoption of the cloud services. So if you are trying to accelerate the adoption of any of the AWS services, they are really good folks to give a call to.
Yeah, absolutely. Thank you, Luis. So with that, I think the conclusion is obvious. SageMaker is a great platform for building, training, and deploying machine learning models. We saw in pretty good detail what capabilities you have for deploying those models to low latency at scale and maintaining them. Luis gave a great description of how they've integrated SageMaker into their workflow at Fox, and you're all invited to go try SageMaker on your own. There's a free tier, so it doesn't cost anything to give it a try and try building your own models. And with that, we'll happily take any questions at the microphones in each of the middle aisles. Thank you.
Thank you. Great presentation. Yeah. I was curious on the deployment of SageMaker models in other contexts, like in on-prem, very low latency scenarios in which there's not enough time to call an HTTP endpoint. What are the solutions or recommendations for that scenario?
Yeah, that's a great question. So the machine learning models that are produced in SageMaker training are saved to your S3 bucket in a file called model.tar.gz. And this is just a tarball. You can uncompress it, and you can see all of the files. And so you can take those and do with them anything that you want. So for if you wrote your own code, then interpreting that model file will be as easy as understanding your own code, which hopefully isn't very hard. If you're using a Amazon first-party built-in algorithm, then many of those are based on open source. So XGBoost, for example, you can just use the open source implementation of those models. The linear models are also very interpretable because it's just one weight for each input that you supplied. So you have full control over where you can deploy these models. If you want to deploy it on your own application server, because you need microsecond latency instead of millisecond latency to hit an endpoint, then you're certainly welcome to do that. Great question. Yeah.
Hi. Thank you so much. It was an awesome talk. So I have a couple of questions. First of all is like when you say like you can auto-scale your model execution, are you talking about model execution in parallel, or like it is basically taking a multiple request and multiple requests are going to different instances?
Yeah, so it is horizontal scaling. So the scaling is adding more machines to the fleet behind a load balancer. So each request to the endpoint still gets routed to a single instance.
Okay.
And will only get executed one time. There's no capacity to take a request and split it up across a variety of machines. So if you need more compute for your hosting, then we support vertical scaling. So you can turn on a P3 16XL machine for hosting with 8 voltage GPUs and 64 CPU cores if you need to. But if your model doesn't run fast enough on that, you'll have to get creative.
Okay, so second question is like, so Spark MLlib, so they actually have some model execution which runs in parallel in multiple nodes, right? So is there any integration point where like SageMaker and Spark MLlib work together or something like that?
I'm going to look at you on the Spark question.
We actually do that very often. So we switch back and forth between built-in SageMaker models and MLlib models, which is the machine learning library that comes out of Spark. And I mean, at that point, your SageMaker instance is kind of a hosted notebook instance. So if you have that notebook instance connected to SageMaker, to your EMR, you can build your machine learning model using MLlib. And then if the output of that model needs to be fed into another SageMaker notebook, you can use the SageMaker PySpark library that I just mentioned. And within the same, even within the same notebook, you can go through that back and forth between MLlib and SageMaker and all that stuff.
But that cannot be deployed to the production or endpoints, right?
No. So, I mean, no and yes, because you can always take that code and package it into a Docker instance once your model is trained. So you can use MLlib to train your model at scale. But then once you have trained your model, those parameters can be packaged into a Docker instance. Then you can deploy at a scale using the container framework that comes with SageMaker.
Thank you. Thank you so much.
Hi, Luis. Great talk. Quick question. You said that you were starting with SageMaker notebooks and you're calling into EMR to do the data wrangling. Have you thought about doing the other way around in terms of running Jupyter Hub off of the EMR, getting into the notebooks there and making calls out to SageMaker? Did you evaluate it in that direction? And was there any pros and cons in either direction?
No, I mean, we pretty much went through SageMaker as a starting point because we saw that SageMaker came with all those optimized libraries. So that's where we started. And then we realized, once we started in that route, we realized that data wrangling was an issue. And then we added all these extensions to be able to overcome those issues.
Right.
But yeah, we haven't evaluated the other way around because that's the way we started.
Okay, great, thank you.
The other way around would totally work, right? If you have whatever code running in EMR, whether it's a notebook or a cluster, you can make API calls into SageMaker from there, either to launch training jobs or to make predictions on pre-trained models. It doesn't really make sense to make an API call into a notebook instance because those are really integrated development environments. But to any of the other SageMaker services, you can totally call into those from EMR or Batch or Lambda or any other computing environment that you want.
Okay, great, thank you.
I had a quick question about the hyperparameter tuning. It's a fairly new feature, is that right?
It was announced with SageMaker a year ago at reInvent and has been generally available since June, if I remember correctly.
Okay, is it possible to get the statistics or any of the data that's happening behind the scenes? Say you want to get out of sample predictions to do confidence interval testing in bootstrapping. Is that can you get to that, or you just run this? It runs the parameter, gives you the best one, and that's it.
So the hyperparameter tuner uses a technique called Bayesian optimization, where it builds a machine learning model to predict the quality of your machine learning models, and the kind of Bayesian optimization we use creates a model called a Gaussian process. Which is a very data efficient model, so it trains well when you have 10 or 20 training data points. The exact configuration of the GP model that is used is not exposed because it's constantly being tweaked and improved. Honestly, like if you got the details of it today, and in a month the scientists would have tweaked its behavior and those wouldn't mean anything. But the data that the GP is trained on are all transparent to you, and in fact data that your training code generates and is emitted to CloudWatch metrics. So every hyperparameter tuning job and now recently every SageMaker training job can emit algorithm metrics, which track things like the loss on the training and validation sets, or whatever other quality metrics you might want. And those are sent to CloudWatch Metrics in your account where you can see them. And those are the metrics that the hyperparameter tuning model is trained based on.
Okay, so you can get the statistics on each iteration then as it's learning.
Sorry, can you speak closer to the microphone?
You can get the statistics on each iteration as you're doing your sequential.
That's right, and you will see, so every training job that happens as part of a hyperparameter tuning job happens transparently in your account. You get the full log of it, you get the model that's created from it, you see everything about it. So yeah, you get all of those statistics, which, yeah.
Great, thanks.
Yeah.
Thanks very much. It's very interesting implementation between the two technologies. A question about how the predictions work. So if you have sort of data wrangling that's occurring within the Jupyter layer of SageMaker, and then you want to run like a real-time prediction or even a batch prediction, does that mean that that's then pointing back to this EMR cluster that's continuously running in order to perform the data transformations that are required for that prediction?
That is correct. So a lot of the jobs that we've been dealing with at this scale have been mainly batch jobs, but we have started experimenting with a few real-time ones, and we have a continuously running EMR cluster that leverages that we leverage to pre-process that data at scale.
So pre-process, do you mean that the data wrangling that occurs within the Jupyter notebook also has sort of a layer of implementation that transforms the data in preparation for the batch prediction process?
No, sorry. I'm talking about when you're doing real-time predictions, those real-time predictions are being executed in an EMR cluster. Sorry, those real-time data preparation for your feature engineering are being done in the EMR cluster.
Got it. Okay. Mm-hmm. And then a follow-up question about the way that you think about data wrangling for data science. Mm-hmm. Do you have the concept of sort of that data scientists may perform transformations that are valuable to have at a higher level or maybe at an earlier level in the data lineage that would be transformations that you would want to promote to maybe like a data warehouse layer or something like that?
Yeah, I mean, as I mentioned at the beginning, our reason to go through this architectural decision was to limit our dependency on the data engineering team, especially on the development side of things, right? As we're doing data science modeling, we don't know what features we want to use, so we want to go through as many experimentations as possible, so it's not feasible to have to give a spec to the data engineering team every time we want to make a new experimentation and say, hey, this is what we want, can you create that so that we can fit it into our model? So this allows us to iterate a lot faster. And once we have a well-defined data transformation job that gives us the features that we want, that work well, that we want to deploy into production, then at that stage we give it back to the engineering team to productionize it. But this mainly helps us a lot in improving those iterations during the development of our models.
Excellent, thanks very much.
And I'll add an alternative to the data wrangling for prediction, which is some customers who do similar workflows to Fox. When it comes to prediction, they will bundle together the data preprocessing code and build a custom container for prediction, which first does the transformation using the Spark system. mLeap is a package that's often used to do this for low latency. And then it'll bundle together that preprocessing code with the learned model and deploy it all inside of a SageMaker endpoint. So it's an alternative way of doing it.
Okay, thanks.
Right. Yeah. Quick question on the same topic. So what if the data wrangling and the transformation is done outside AWS? So basically, it's not within the AWS stack. Have you ever come across that kind of use case from a customer? So like, how would that integration look like? Because then you won't be able to integrate it with the EC2 machine.
Yeah, and if you're doing data preprocessing on-prem, for example, or maybe inside of your database or data warehouse, for example, before loading it into S3 to use it with SageMaker. This is common and normal, but there's and very useful and important sometimes, but there's an opportunity for bugs because you need to replicate those data processing steps in your prediction code in order to achieve the same results. So, you can do it. You just have to be careful and test to make sure that the data processing that you're doing at prediction time matches what you were doing at to prepare the data for training. And in that sense, it's, I don't know, I would say it's maybe not the best practice because this is an opportunity for bugs to creep in if you have separate code paths for doing those data processing steps, which are supposed to be having the same result.
Yeah, because data processing would normally include integration with multiple data sources as well, right? So, like even that would then need to be included in the same code. Yeah,
I mean it's a reality, right? Like you have to do it sometimes, but it's just something to pay attention to and be careful with. Like test it well, feed data into both systems, make sure you're getting the same results out, and then it should work.
One thing that I'd like to add to that is that, for example, we use S3 as that integration layer in a lot of situations like the one you're mentioning. So if we have data from multiple data sources, we will create those exports, put them into S3, and then utilize that EMR cluster, or if the data is not that big, then SageMaker directly to be able to wrangle that data together to be able to fit it into our model. Or even sometimes if your data is already prepared, you just point your SageMaker model to that S3 location that contains your data in CSV format.
So after integration, do you bring the data back into S3?
Yeah, so imagine that you have 3 different databases and each of them have a subset of data that you want. You can always create a job that exports from those databases the subset of the data that you want, put it into S3, and then leverage EMR to wrangle it all together, create your training set and your validation set, and fit it into S3.
Got it. Makes sense. Thanks.
I think we can take one more question. We're just about out of time.
So after last year's reInvent, did some playing around with SageMaker and felt like there were some boundaries around it, and it sounds like that's what you guys encountered and went through quite a bit of a hackathon experience to make it work with other things. I'm wondering what AWS has learned from experiences like theirs in what they might be applying to SageMaker going down the road to kind of knock down some of those barriers.
Well, so we're always listening to our customers as far as what they're using our products for, how SageMaker is working for them, and some of the challenges that they're running into. And so yeah, we absolutely are making improvements to make it easier to use, integrating it more seamlessly with other AWS services. If you have time after this, I'd love to hear some specifics about some of the things that are causing you problems. But we know that we're constantly innovating with it and working to improve it, make it easier to use, add new machine learning capabilities, and you'll be hearing about those coming up very soon. But with that, thank you all for your time, and thanks. Enjoy the rest of your week.
Thanks so much.